All right, welcome to another week of the Chem 1211 lab here in North Georgia. This week we're going to be taking a look at the enthalpy of neutralization. So taking a look at just really kind of a simple neutralization reaction and looking at kind of the energy involved with that process and ways we can try and measure that. So there's going to be a lot of similarities between this lab and kind of some of the things you were doing experimentally a couple of weeks ago with specific heat in terms of some of the calculations and some of the equations that we're going to see and even some of the experimental setup in the case of the calorimeters. But I do want to kind of talk about some of the things that are going to be a little bit different this time around. And as a starting point, we are talking about enthalpy here. So the enthalpy change for a reaction. And probably one of, I think, the best ways to think about enthalpy when you hear that term, it's the energy change via heat during a chemical reaction. Now, where that energy change kind of comes from is the fact that when a reaction takes place, you're going to be breaking some bonds that were already in kind of your reactant molecules and forming new bonds to make your products. And in that process, it's always going to take energy to break those bonds that are present in your reactants, and then you're always going to get energy back as you form your new bonds for your products. And your change in enthalpy overall is really just the change in energy that happens kind of from this process. And so when you sum kind of all of that energy that's kind of put into breaking bonds and then the energy that you get back from forming them, that's where your kind of enthalpy change for your reaction really comes from. And so when you think about enthalpy, like I think that one of the best ways to really think about it is to think about the energy involved with kind of those breaking and forming of bonds in that reaction. Now, in terms of ways we can calculate enthalpy, one of the things we do want to be aware of, it is related to heat as well, right? We said in the kind of up the top of the slide here, this is an energy change via heat. So at constant pressure, which is going to be most situations in lab, unless you're in some kind of really enclosed system for some reason, our enthalpy change should always be equal to just Q, like the overall heat change itself. And so when we're in particular going to be calculating our enthalpy of neutralization, like when you start doing it for very specific reactions, particularly if you have a balanced reaction that you're looking at, a lot of times what you'll end up doing is you'll taking the actual heat for that reaction, the Q that you can measure, and we'll go over how to do that in here in a little bit too, and divide it by the moles of your limiting reagent in that reaction. Because the normal units for this enthalpy of neutralization here are typically going to be in kilojoules per mole. It's probably the most common units that you'll see that in. And so it's per mole because it kind of standardizes how much energy change is really happening and gives you kind of a reference point, because the energy released or absorbed is going to be different depending on how much reactant you actually reacted. And so that's kind of what this is accounting for, is that we're kind of standardizing so we have a general energy change that's happening based on a certain amount of compound that's reacting. Now, kind of experimentally, what we're going to be doing here and how we're going to find our enthalpy, we're going to use calorimetry similarly to what we did back in our specific heat lab. Remember previously we could find the heat that was lost by a metal by looking at the heat that was gained by the water, and this idea of calorimetry is being able to track the heat kind of on both sides when you're gaining or losing it. We can do something pretty similar this week. What we're going to be looking at instead is we're going to be looking at heat that's being absorbed by the water to help us find the enthalpy for a reaction. Because basically all of the heat that's being absorbed by the water has to actually come from the reaction itself. And so if our goal is to find this enthalpy of neutralization, or here I have it just as delta H of our reaction, which is really just Q of our reaction over the moles of our reactants, whichever one's limiting. If we want to find this Q of our reaction, what we can do is if we do our reaction and look at the temperature change of the solution that's happening, we can basically figure out that the heat given off by our reaction or the heat absorbed from our reaction is going to correspond to the heat basically that's going to be involved for the water and just kind of the calorimeter and the general surroundings. Remember a week ago we talked about this calorimeter constant idea that we could use to find the heat of our calorimeter. We are going to be doing that again this week as well, just trying to account for kind of in a real scenario, like trying to track and make sure we're keeping track of all of the heat and energy transfer that's really going on in the system. Now, experimentally, there's going to be two parts to this experiment. The first part of this experiment is actually going to be to determine the calorimeter constant. So we didn't do that the last time we did calorimetry. We are going to do that this time, and we'll go through how to do that in just a second. And then once we figured out the calorimeter constant, then we'll have all the pieces we need to find the enthalpy of neutralization. We'll kind of look at what are the actual individual experiments for each part, and then also we'll go over some of the calculations for each here as we go. So for the calorimeter constant part, what you're going to be doing from an experimental standpoint is you're really just going to be mixing hot and cold water. So typically you're going to take some water, probably just in like a beaker, and you're going to heat it up. Just on a hot plate is fine. It doesn't have to be a Bunsen burner or anything crazy. And it doesn't have to get really hot. Like you don't have to get it boiling. Just even if it's like 40 degrees Celsius or so, that's plenty hot. We just want to get the water well above room temperature. And what we're going to do is then take our hot water and we're going to mix it with cold, which really is not even cold water, it's just going to be room temperature water that's going to be in our styrofoam calorimeter cup. And when we pour our hot water into our calorimeter cup, what we should be able to measure is the temperature change of the cold and the hot water as kind of those temperatures equilibrate. And we should be able to figure out then from kind of that temperature change information how much heat is lost by the hot water and how much heat is gained by the cold water. And probably what you should see is that the hot water actually is going to lose a little bit more heat than the cold water is going to gain. And the reason for this is that there's a little bit of extra heat that's also going to be lost to that calorimeter cup and just kind of the general surroundings. And that's the heat we're actually interested in this first part of the experiment, because that's the heat that we're really factoring into our calorimeter constant. And so this calorimeter constant, the way we find this is we're going to find kind of what's the extra heat that was lost by the hot water that the cold water didn't gain. And if we take that amount of energy and divide it by the temperature change of the cold water, since the coffee cup is basically undergoing that temperature change as well if it's holding the water, then we should be able to figure out roughly what our calorimeter constant is. And we can figure out how much energy it takes to raise that coffee cup, or our calorimeter in this case, by that particular temperature amount. And so to give kind of a visual as far as the data we're recording here, and this is straight from kind of your pre-lab reading as well, what we're doing initially, we're going to have hot water, like I said, somewhere around 40 degrees Celsius ideally. Could be hotter, could be a little bit colder, but probably try not to go too much under 40 for your hot water if you can, just so we have a nice temperature difference to kind of look at. If the hot water is only like 30 degrees Celsius, this temperature change isn't big enough, and there can be a lot of kind of weird things that can happen from that. So slightly bigger temperature change, kind of nicer for us to look at. And so what you see here is that we basically have two solutions initially that are at different temperatures, right? We have hot water, cold water. We're mixing them at the end. We have kind of our mixture. And what you're going to do is you notice that as far as the temperatures of these things, you see them kind of slightly changing. You can, if there's a pretty decent slope on these when you're looking at kind of your data points that you're recording, you can kind of extrapolate things to what they are at the exact time of mixing, or what the temperature should have been, like really right after mixing it with the highest possible temperature. The nice thing, we do have LabQuest now that can kind of record way more data points than just what you see here. And so you can use those to kind of creatively get just more data points and have a little bit better idea of what is the temperature really as soon as these things are mixed and everything is kind of perfectly equilibrated and mixed well. It's not going to be what the temperature is exactly at this second, but maybe like right in here, it's much closer to when the time things are actually mixed. But really, once you mix your hot and cold water, you're looking what is kind of the temperature where things kind of equilibrated to between those two solutions. And you can use two thermocouples to kind of figure that out. I have like one thermocouple in the hot water and one in the cold. Mix your two solutions together, put both thermometers in, and kind of see when do those temperatures get to be about the same, or when do they at least both kind of stop changing, because they might not measure the exact same temperature even if they're in the same solution. Now, the second part of our experiment, once you've kind of gone through and you found the calorimeter constant, including what we kind of just outlined, what we're going to be doing now is actually doing the neutralization reaction itself. So that means we're going to be taking an acid and a base that we're going to be reacting. Now, before you react them, I do think you are going to be doing a dilution on the acid solution. So do be aware you are going to have to do a dilution. If you don't remember how to do that, you can probably go back and look at kind of some of your previous labs. We've done that a couple times now this semester, particularly the precipitation experiment where we made I think it was the calcium iodate before, that you can go back and actually, calcium carbonate, you can go back and look at what we did that week in terms of doing dilution calculations to figure out how to dilute your acid solution appropriately. But when you do the acid-base reaction, it doesn't really matter what starts out in a beaker or what starts out in a coffee cup for the kind of general start. All that matters is when you go to mix these two things, you want to make sure they get mixed in the coffee cup calorimeter, because that's what you basically just measured the calorimeter constant for. So you don't want to mix these things in something like a beaker instead, because the calorimeter constant will be very different in that case. But what we're able to do then is when we mix an acid and a base together, most of you probably have an experience of some kind before where you've mixed an acid and a base. The temperature probably went up, it got hot. And so what we're able to do is really measure what's the heat that's gained by the water during this process. We can do that with kind of the same equations we did back with specific heat previously. We can just find the heat for our water is going to be equal to the mass of the water times its specific heat capacity times its change in temperature. And then we can also find the heat that's going to be gained by our calorimeter. If we know this change in temperature of the water, we can take the calorimeter constant that we just found, and that was really the whole point of the first part of the lab, and then we can multiply it by the change in temperature of the water that we observed during the second part of the experiment. And now we have the heat of the calorimeter, we have the heat of the water, and remember it's those two pieces combined that are going to help us find our overall enthalpy of neutralization. And again, visually, just what's your data? If you're plotting anything or looking at your data for the second part of the experiment, your acid and base should both be pretty close to the same temperature, somewhere around room temperature. You mix them together, you should see that temperature spike up quite a bit. And so you're looking for what is kind of that highest temperature after these things have really been mixed together to figure out what's our change in temperature been for that reaction. And then to find our Q for our reaction, right, because if our goal is finding this enthalpy of neutralization, once we have our heat for our water and heat for our calorimeter, those are the two parts we just found. Now we can find the heat of our reaction, which is equal to their sum, but the opposite sign. Because what's happening is if our water is gaining heat and our calorimeter is gaining heat, our reaction lost the heat or gave the heat off. And so if the reaction released the energy, then that means it's going to be a negative heat. And so once we have our Q of reaction, which should be a negative value, then we can calculate our enthalpy of neutralization by taking that Q of our reaction divided by really the moles of our limiting reagent, whichever one we have less of, the acid or the base. And once we've done that, we should have our enthalpy of neutralization, and it should be a relatively large negative value when you go to calculate it. Most enthalpies of neutralization is probably somewhere in the ballpark of about negative 50-something kilojoules per mole. Just to give you kind of a reference point to be thinking about when you go to do your calculations. If you see of an answer it's like 65,000, like that's not that uncommon, because if that's in units probably of joules per mole, so that'd be like 65 kilojoules per mole, which is pretty reasonable. I think the actual value for just a plain neutralization reaction with strong acid, strong base is usually about 56 kilojoules per mole. So that gives you kind of, I think, some good perspective what to expect for your numbers as you kind of wrap up the lab. Right, that pretty much wraps up everything that we have for this week. Like I said, there's a lot of kind of carryover ideas and kind of experimental setup pieces from weeks before. One last note, as far as kind of like safety, waste, things like that, we are using an acid and a base. Their concentrations aren't terribly high, although the acid is a little bit higher concentrated before you dilute it. So do just take normal caution dealing with an acid and a base like we have earlier this semester. And waste-wise, everything can actually just go down the sink, because if everything's been neutralized at the end of your reaction, it's pretty much just salt water. You just have sodium chloride in your water, and you can just pour that down the sink without any problem. So no real special considerations there. Hopefully this video helps get people ready for this week, and we will see you all next time.